Okay, I'm recording. Good. Confidence in the words. So we did the last time, as you remember, we did hypothesis testing. So the question was hypothesis testing is like, why do you do that actually? And the reason for that is because you want to understand how does one mean compare to another mean? How does one mean of your sample compare to the population mean? In the simplest example of a STAT test. It basically, it helps you to make a decision based on a threshold of probability that you have determined yourself. So hypothesis testing, in essence, we're having a sample estimate of a mean. And we're hypothesizing under the null hypothesis that the sample mean is identical to the population mean. And then we're calculating the probability that this is really indeed different from that population. You know, easier. So basically with the p-value, you're basically quantifying the probability that this still comes from the same population and the same distribution and is still not significantly different from the population mean. And you're doing that by calculating a difference between your sample mean and the population mean, and you standardize this difference by the standard error of the mean, where the standard error of the mean essentially is the standard deviation of the population, so the variability found in the population, divided by the square root of the sample size. So you're relating the variability of the population to the variability of your distribution of the sample means, this hypothetical distribution of hypothetically drawn samples from your population, where you get different mean estimates, and you assume that based on your mean, based on that sample that you have drawn, you assume that there must be a distribution, a variability around that mean, your point estimate of that mean, that basically follows and associates by standard deviation divided by square root of the n to your population standard deviation. So you mean to estimate this variability of your means. Then you calculate the difference and you use the standard error of the mean to standardize it and thereby quantify the probability that your sample is indeed significantly different, or it's still from the same population and it's not significantly different from the population mean. So you're moving away from standardizing populations. It's not individual scores anymore. It's not individual blood pressure measurements or whatsoever. It is probabilities you're dealing with at this point. So the problem with the hypothesis test per se, it gives you a binary answer. It gives you a yes or no answer. It gives you, in case of a p-value less than your acceptable type 1 error, the so-called alpha, a significant yes. It gives you the answer that this sample is significantly different from your population mean. But it takes away a lot of information. It takes away the information of variability. And Nolan and Heinzen wanted to illustrate that using a meta-analysis that was published in 1990 that actually is, so I got out the actual publication because I thought it may be interesting for some of you to read up on it. So it's a meta-analysis that basically compared, basically incorporated all studies that have to this date in the 1990s studied whether women are better in mathematics as compared to men. So now, debatable thought, but some earlier studies have shown they are, some others have shown they're not. So the meta-analysis is meant to quantify that. And they concluded that the differences are essentially very, very small. And only the extreme tails of the distribution actually were slightly different because some of these significant results showed a significant difference, but overall they were kind of still comparably distributed. They found some differences in terms of task administered to the students or to the participants. They found that females were better with computation and males were better with problem solving. So I'm not a psychologist, I can't comment on this. I've seen enough in my life that I don't think there's a real difference between women and men. when it comes to mathematics and statistics. But so these are the insights from the meta-analysis. But the reason why I'm actually showing that and why they want to show that is that a lot of these dichotomized findings where you say like one is better than the other, it's basically a comparison of means, right? And it doesn't tell you much. And I made this point in one of the earlier classes where I said like the most important thing is when you interpret a research finding is to not only look at whether this is significant or not, also try to understand the variable you're looking at, try to understand what you actually mean to question using this research question, asking these research questions, and also try to understand the variability, the distribution of what you're actually comparing. And when you look at this, so this is the small difference. So when you see, so here we have the mean, right? The mean between two populations. So you have that population is here and that population is slightly shifted upwards. So you may see a significant difference in the means, which is with a large sample size, something that you will see quite frequently, which is one of the biggest issues actually in my work, because I have this huge data sets. It's like I see a difference for everything. Is it really meaningful? Maybe not. And this is why variability is important, because when you take into account variability, a majority of these people, these participants in these two distributions are still absolutely comparable. The only thing that's getting interesting, and these are the so-called outliers, and this is why these are so absolutely important to understand, because yeah, maybe there was a Nobel laureate more in one group versus the other, and maybe there are some that did not further their mathematical understanding. So the outliers kind of may differ. And arithmetically, these outliers obviously matter in statistics. So that's kind of the idea when Nolan and Heinzen thought it was important that you understand that the quote unquote new statistics, a term I haven't heard before I started teaching that book. I knew these terms. I've never heard of new statistics, but now I know about new statistics. So new statistics are basically, that's a term that was termed by Cumming in 2012. And he advocated to look more into the background behind hypothesis testing. Understand the variability, understand the effect sizes, understand the confidence intervals, and pay attention to meta-analysis or conduct your own meta-analysis on topics if you're interested in that. So that basically is being meant with this example and showing you this example. So pay attention to effect sizes, confidence intervals, and meta-analysis, and these are the things we're going to do today. We're going to discuss these components of the new statistics. So let's start off with confidence intervals. So when you draw a sample, you assume you do random sampling from a population, and you have that sample, and you quantify the mean blood pressure, the mean weight, the mean lipid levels, the mean mathematical understanding whatsoever. You get with this mean a point estimate of that population mean. That is your starting ground. You try to reflect in your sample, you try to kind of reflect that population mean, estimating it by quantifying some metric in your sample. But it's not just a point estimate that basically gives you all this information. We just talked about variability being important and the shape and the size of that distribution being important. So therefore you can go a step further and basically bring the point estimate on the level of an interval estimate. An interval estimate is basically based on a sample statistic and provides a range of plausible values for the population parameter. Good. So it's a range of plausible values reflecting your population mean. And this is where I'm switching slides. And these are the extra slides that I have posted also on Canvas. So just let's for a second, and I'm not doing this to totally confuse you, Let's go for a second back to the central limit theorem. So we know that there's a population that has a wide distribution. Then we have a sample, a distribution of the sample means that's very skinny. And it's basically hypothetically distribution of the means from hypothetically repeatedly drawn samples that were assessed and that are basically surrounding that sample at hand that you mean to compare to your population. So it's a hypothetical construct, but it shows it's much skinnier, and it basically meant under the null hypothesis to reflect your population mean. So number one central limit theorem insight is the mean of the population and the sample distribution are identical. Secondly, that distribution around your sample mean is basically the standard error of the mean, which relates to the standard deviation of your population by the square root of the sample size, right? Thirdly, the sample size will have strong influence on your standard error. The larger the sample size, the smaller your standard error. That means if you have an estimate of a sample of 100 people, this will be a more accurate estimate as compared to a sample of 10 people. Conversely, if you sample 10,000 people from a population, you have a very accurate estimate. So sample size matters, and it will decrease the standard error of the mean, because with every accurate assessment, if you have equal samples of equal size, each assessment is going to be much more likely to be accurate as compared to one that is small. So that's conceptually how that relates. So now when thinking about confidence intervals, so we talked about the point estimate. We said like this is one number. This is our best guess for a population parameter. Based on our sample, we think that's the population mean. An interval estimate gives you a range of possible value, gives you the margin of error within which you're operating based on your sample size. And this essentially is calculated in a way. You remember the bell-shaped curve, and you remember the extremes that constitute 2.5% on each side. So just to put this back in your memory, this is exactly this distribution. This is your sample. This is your mean. These are your so-called critical values of minus 1.96 and plus 1.96. To the right of plus 1.96, you have 2.5%. To the left of minus 1.96, you again have 2.5%. In total, this builds up on a two-tailed hypothesis, the 5% of a critical threshold, a critical value that basically is consistent with the so-called alpha, or an acceptable type 1 error. That means as soon as your difference with the set testing, we calculated the difference and we standardized it by the standard error of the mean. So as soon as your difference fell beyond one of these thresholds, it was significantly different, right? Remember that from last time. So now, if you wouldn't calculate the difference and you wouldn't subtract the population mean from the sample mean, and you would just characterize your sample with these two thresholds, you would get an interval within which you basically would find, given the null hypothesis were true, your population mean. And that makes you, quote unquote, 95% confident that you capture the population mean. Yes?
Is it 95% because of the z-score?
Yes, the z-score of minus 1.96 and plus 1.96.
It would be like 68, 95, and the other one's 98.
Not the standard deviation. So we're looking at the standard error of the mean. So it's now probabilities, right? And we have the z-score table. Remember the z-score table, this confusing table with a lot of percentages. So 1.96 corresponds there with 2.5% and 2.5%. So it's the 2.5% on both sides, on both tails. So now you can calculate these confidence intervals as an upper bound and a lower bound. And you're doing that by either subtracting or adding 1.96 multiplied by the standard error of the mean to your sample mean. Gives you two values. If you, let's say you have blood pressures, you have blood pressure here, blood pressure there, you are within these 2 points, within these intervals, you're 95% confidence that you're capturing that population mean. And if it's in there, your null hypothesis is true. If it's outside, you're rejecting the null hypothesis, and it's significantly different. And to illustrate this also arithmetically, you remember that example we did last time. So you conduct a STAT test on a sample for which you observe a mean weight of 150 pounds. The population mean is 160. And the standard deviation is 100. So you want to do a STAT test. And we've done that last time. So essentially what you do, you use this formula and you see whether the standardization of this difference here, the numerator, is the difference between the sample mean and the population mean. And you standardize it by the standard error of the mean, which is standard deviation divided by the square root of the n. If this standardization is exceeding 1.96 or minus 1.96, it's anywhere beyond these two critical values, then you have a p-value less than 5%, which is your quote-unquote alpha, your acceptable type 1 error, and you will reject. If not, then you will accept the null hypothesis. So let's quickly write this down. We have a mean of 150. We have a standard deviation of 100. We have a sample size of 300. Let's take example B. And now we want the standard error of the mean. This is basically standard error divided by square root of the sample size. Is 5.77. Now we want the STAT test, STAT score, which is now basically the difference between mean of 150 minus 160, which is the population mean, divided by the standard error of the mean. So that's a STAT score of minus 1.73, which, if we're going back now to our thresholds, it's minus 1.96 or plus 1.96. It's not exceeding that critical value. Thereby, we are accepting the null hypothesis and not rejecting it. If we were to express this now differently with 95% CI, we would essentially, so 1.96 is our threshold. That's the alpha that we're willing to accept. Then we would basically calculate 150 minus 1.96 multiplied by our standard error of the mean. So that would be our lower bound. That would be the upper bound. The upper bound would be 150 plus 1.96 multiplied by the standard error of the mean. So this essentially gives us two values here. This gives you a lower bound and an upper bound, 139 and 161. So this is the area within, given the standard deviation and the standard error of the mean and your mean, within which you're 95% confident your population mean would need to be located in. If it's not, it's significantly different from your sample. So this is basically, it's almost like a different way of hypothesis testing, and that's how you can employ it. And you can do the same with a 99% confidence interval, where you're just exceeding that interval. You're just increasing the interval. You're basically going 0.05 on the left side and 0.05 on the right side. And that gives you a STAT score, a corresponding critical STAT score of 2.58. You can also do a 90% confidence interval, which would be 1.65 multiplied by the standard error of the mean. Or you can do any other set score, whatever confidence you're interested in. But you can use this to describe the confidence within which you're certain your population mean is in there. So it's basically inverting the hypothesis testing. And why is that? And this is the way you have to look at this to understand now how this suddenly became such an association with probabilities. So you remember I talked about this randomly drawn repeated samples, and we're building this hypothetical distribution around our mean. And I've been talking about repeated samples that have been drawn. And this is how you have to look at this. You have 100 samples, and out of the 100 of these random samples that you have drawn, 95 would contain the population mean. And this is depicting it. So you have here the population mean indicated as the blue line. You have here the first sample that was drawn with a calculated confidence interval from the left end of that line to the right end of that line. Does contain the population mean. Second one also contains the population mean. Third one also contains the population mean. Fourth one does not contain the population mean. So that's one of the 5 that basically fell out. That does not contain the population mean. So it's significantly different from the population mean. And so this is the definition of the confidence interval. So you get a mean, you have a sample, you have a mean, you have a point estimate, you build around the confidence interval, and that gives you that interval within which you are certain to capture in 95% of all times that population mean. So that's the definition of the confidence interval. Any questions on that? I know it's quite a challenging topic, but it will become super clear moving forward. Good. So if you want to understand the concept in more detail, I highly recommend this slide because that's a very powerful depiction, essentially. Good, but let's go back. Let's hypothesis testing. So now we have a point estimate and an interval estimate. We've discussed our confidence interval. Nolan and Heinzen has a slightly different way of calculating it, which is not going to be a dramatic difference. But they're basically using a formula where they're basically having a negative set multiplied by and adding twice the mean, which arithmetically comes to the same end, but I just don't like it that much. I rather like to subtract negative things from positive things. But it's the same calculation, again, same concept. It means to describe these tails, below which and above which you basically have in total a 5% probability of not having the mean included. And yeah, so they're doing the same exercise. Good. Any questions with this so far? Secondly, we're moving now towards effect size. So we're having now a formula that allows us to calculate the set in hypothesis testing, right? So we're basically looking at 2 components of this set. One is the numerator, which is the difference between the sample mean and the population mean. The second one is the standard error of the mean. We're basically calculating the difference and we're standardizing it with the standard error of the mean. This will give us a set which will then allow us to either accept or reject the null hypothesis. Again, this set beyond which we are rejecting is determined by the so-called alpha level. And the alpha level is usually based on a 5% threshold, which is the minus 1.96 and the plus 1.96. Usually, there are deviations to that in some research questions. Good. So now one problem we have is the standard error of the mean. The standard error of the mean is related, as shown before, to the standard deviation of the population by a division by the square root of the sample size. That means if you have a larger sample size, your standard error of the mean is going to be smaller. If you have a smaller denominator with an equal numerator, you will have a larger set score. If you have a larger set score, you're more likely to reject the null hypothesis. That means sample size is your friend in some regards, because it basically will allow you to more likely find a significant set score. But it kind of misleads, because you're paying all you're drawing all the attention on the standard error of the mean and the sample size, but not really on the difference. So you may not understand the difference and what it actually represents in your analysis. So the effect size is essentially now a way to look at this in a way that is not as strongly affected by the sample size. Because effect size as a concept, the effect size is basically that area which does not overlap. In a comparison of two populations, the area that does not overlap is essentially that area that is the real effect size. So you're looking at two different comparisons. So you have an effect size which is determined with equal variability, basically determined by an increase of the differences. So both of these have the same distribution, but you see the faint line basically showing two, yeah, it's very faint, showing two different differences. So these distributions are further apart, which will then basically will be reflected by a greater difference, or a larger numerator. If you have the same difference and the same means, the same group means, but you have less variability because of a larger sample size, you also have less overlap, right? Because the overlap lowers your probability of a significant difference. So therefore, you need something to take sample size out of the equation. And this is being done. So, okay, so you can increase this effect size by moving the means further apart, increasing the intensity of an intervention, or choosing more extremes in the population distribution. Or secondly, you can also do it by finding smaller variability, which would be the increase in sample size. You can estimate effect size with Cohen's d, which basically takes the sample size out of the equation and puts the weight on the difference. And this is done because sample size is such a strong influence, because getting differences larger and altered is a rather complex thing to do. So you calculate Cohen's d by standardizing the difference between the sample mean and the population mean by the standard deviation this time. And please memorize that, because that's quite a trap on the quiz. And you will be asked for effect sizes quite frequently on the quizzes. You will see. So basically the standard deviation remains unaffected by the sample size, whereas the standard error of the mean is clearly affected by the sample size. It will have a very strong effect on your set estimate. So you're standardizing it for the effect size, and only for the effect size, not for the set, by the standard deviation. And you will then, in the next step, you will basically go and compare your derived effect size, and you will do all of this for the quizzes. You will basically interpret the effect size based on the convention by Cohen, where basically a small effect size would be 0.2 to 0.5. A medium effect size would be 0.5 to 0.8, and the large effect size is everything greater than 0.8. And the respective overlaps of your two distributions are reflected here. So you have with the small effects as 85, with the medium effects as 67, and the 53 with the large. 53 or less. Any questions on effect size? So basically you mean to take the effect of a sample size out of the equation. You mean to kind of put the weight on the difference between the populations. If not, then we can move on to meta-analysis. So it's quite a complex class today. It was quite a lot of material. That's why I thought that repetition class on the topic on Wednesday will be a good idea. So meta-analysis essentially involves the calculation of a mean effect size from the individual effect sizes of more than one study. So basically in research, one of the major principles is that you always need to replicate your results, your studies. You cannot just make decisions on a large scale and extrapolate the findings from one study to the entire population by just having one study result. So you always need to replicate results. You always need to replicate studies to essentially see whether the results are consistent. And to be honest, they're not always consistent. They're quite frequently not consistent. And there's this variability between study results is also what is quite some causes controversy at times. So therefore, meta-analysis is essentially regarded as the highest available evidence in research because it basically amalgamates the results of each individual study. So there's actually a group in the UK, the so-called Cochrane data group. The Cochrane group, essentially, they're having funding from various institutions and the government. They're basically doing nothing else but meta-analysis. So they're basically taking studies, they're reading studies very detailed, they're characterizing those studies. They do what is called a risk of bias assessment. So they're also grading the risk of bias within the study. And then they're basically taking those results and putting them in meta-analysis. So if you Google them online and you're interested in one particular topic, you will find in the Cochrane topic for almost every relevant topic in medicine and psychology. And this essentially, they have reports that are like 100 pages long for every topic, basically amalgamating all insights from all of the studies that have been published. And these meta-analyses essentially are quite complex on many levels. So they are complex because there's a lot of variations between the studies. There's a lot of heterogeneity between the populations. And it's, bluntly spoken, it's quite complex to basically calculate an overarching, globally applying estimate for various different insights. However, it provides added statistical power because you consider all these studies simultaneously in one estimate, and it sometimes helps to resolve debates fueled by contradictory research findings. But it also sometimes also adds to the debate, not necessarily the most helpful manner. So it's research is basically, you can never say something with certainty. And meta-analysis is just one further step in the toolbox to basically get us closer to make determinations based on the highest level of certainty. But there's never 100% certainty. So you basically, in meta-analysis, you select the topic of interest, you decide exactly how to proceed. That's already quite complex. Locate every study that meets the criteria. So first, you basically determine the so-called PICO criteria. PICO stands for population, intervention, comparison, and outcome. So you will find studies that are matching your PICO criteria. Then you will locate every study that meets the criterion, and that's a lot of work. Trust me on that one. So you scout through PubMed, Medline, M-based, so you try to get every study that to some extent relates to the topic. Per day, I believe PubMed publishes somewhere in the realm of 10,000 studies. So you need really good algorithms to weed out everything that is being published and find only that is pertinent to your research questions. Once you have every study, you do a risk of bias assessment, and then you extract the necessary data you will need to calculate your effect size or whatever other metric you want to use. And then you move on and you calculate the statistics. I don't know this paper, but they probably give you an idea how to calculate effect sizes. But you can quantify various matrices. You can do relative risk, incidence rates, you can do odds ratios, hazard ratios. So all kinds of different matrices can be used to be analyzed in a meta-analysis. Okay. Considerations, check availability of statistical information comes back to that point. So not every study makes it in your meta-analysis because they may not be reporting the data you actually need. You need to select studies in which the participant criteria are met. That's your PICOS criteria. And then you need to eliminate studies based on research design. Sometimes studies are not designed in a way that they help you, or they're just poorly designed generally. So you have to exclude those. Just to give you an idea, when it comes to preparing meta-analysis, the one I mentioned, so I worked on a meta-analysis for the last 15 months. I'm presenting it actually later this week at a conference. We started off with 3,600 papers, and right now I'm going to present a meta-analysis based on 19 of those. So that's how much work that is. It was 15 months of work. So it's quite involved. But that's what you essentially end up. At the end of the day, this is what you want to see. You want to see a so-called forest plot, where each of these studies represent one of those branches of your forest plot. So you have here different studies, and you have estimates of the effect size. You have estimates of your effect size shown here as an error bar. So you have here the estimate, and you have the 95% confidence intervals indicated around that estimate. You have here numerical representation of that effect size. You have, again, the 95% confidence interval. And as you can see here numerically, there's a lot of variation in these estimates. And that's also where it comes down to getting then an amalgamated estimate, incorporating all the studies. To be honest, they are saying it's a mean of all the effect sizes, which couldn't be further from the truth. It's a very complex model that is being built nowadays. Maybe it was different when they wrote the book, but nowadays it's a random effects model that basically incorporates a lot of information, including these estimates, but also the variability, because the variability also matters. And nowadays we have more advanced analytic methods that basically allow for us to incorporate also the information of variability in the models. Good, but this is a forest plot. This is how a meta-analysis looks. There are variations to that, obviously. There are different graphical ways to depict it, but this is basically what you're looking at when you look at a meta-analysis and on a forest plot. In the same context, there's also an interesting thing that is done in addition to that. So meta-analysis, you can also depict these estimates in a certain shape or form that kind of will help you understand whether there's a publication bias. There are different biases that can be quantified. Publication bias is a good one. Another important one is the so-called file drawer analysis. So when you think of a study where somebody has done a lot of work on conducting a study, has worked on that study for years, and then there was no significant result in that study. What's going to happen with that study? It's going to end up in a file drawer. So what the file drawer analysis essentially wants to show is how many studies that did not show a significant effect did actually end up in a file drawer, and how many must have ended up in a file drawer to essentially take this estimate to move away from a significant estimate to a non-significant estimate. So how many studies that have been a negative result or a null result would have needed to disappear in the file drawer to actually make this result non-significant? That's a file drawer analysis. So you basically quantify that number of studies with non-favorable results you would have needed to see. And if that exceeds the number of published studies, you can conclude that likely there's a problem. But yeah. So usually it's not really the case that studies end up in the file drawer. Sometimes they do, sometimes they don't. There's actually, in the meanwhile, a journal that focused exclusively on publishing data and publishing articles that showed negative findings. Because the community has become increasingly aware that file drawer analyses are a problem, and more papers are not being published because all the journals only want to see significant results. They want to see something that makes a change, right? Because it creates more attention from the community, it increases and helps to increase the impact factor of the journal. So they're more favorable towards articles that show a significant result. So this being said, the file drawer analysis, no, actually, so this journal for publishing negative results actually is quite a tendency to counteract this. So they are exclusively publishing negative results. Just that the data is known and it can be included in meta-analysis, and it helps the progress of science. Good. Any questions to meta-analysis? File drawer analysis, negative findings? And very much to my surprise, we're getting to statistical power. So, not a pleasant surprise. Good. So we have discussed a type 1 error. We have discussed the type 1 error as an acceptable error if it is not exceeding that 5% threshold, the so-called alpha. So we have with the type 1 error, we have an error where we're actually rejecting something that should not be rejected. So that means you have a sample drawn from your population, and you have a certain risk that you are rejecting the null hypothesis of this sample mean being identical to your population mean. And there's a certain risk that you're rejecting something that you shouldn't have rejected. And this is called a type 1 error. So this is, so to say, a false positive. If you are not rejecting what should have been rejected, so let's say we fail to reject the null hypothesis, although in truth an effect exists, we're looking at the type 2 error. A type 2 error is a false negative result. So both are equally problematic, right? So I'm flagging this table. I think that's a very important table. Like, make a note that you find it again. So the type 1 error is essentially, why is that problematic? Because you see a significant result. You're concluding something on something that you shouldn't have seen. And you may hypothetically harm a patient, right? If you see a significant difference that you basically think this is favorable for the patient, this may be very harmful for the patient moving forward. So that may, if you roll this out on the Medicare population and you build your insight on a type 1 error, this can be having some very adverse consequences. Secondly, you have the type 2 error. When you have a type 2 error, you're not seeing a difference, although you should have seen one. What's the problem with that? You may not conclude that you should do a certain intervention, but you may hypothetically also waste a lot of money on an incomplete or inaccurate or not well conducted study because your quote unquote power calculation was not well enough and you studied not enough people, because a large sample size will lower your variability, as we have learned. And lowered variability may give you a more accurate estimate what's really happening, and that may have avoided from you not seeing a difference that you should have seen. So it means to avoid essentially to lose this information and to save a lot of tax dollars, because essentially power calculations for NIH studies, these are double checked, triple checked, quadruple checked, because it's just important that every money that is spent on research is well spent and you're not conducting a study that is underpowered, right? So then you have basically, so you have reject the null hypothesis and you're rejecting it because it's true. That is a correct decision to do, which essentially is adding up. So you basically, in truth, you have an effect that exists. The probability for determining that is 100%, right? Either you don't see it or you see it. If you see it and it's there, you should have seen it. If you didn't see it, you basically lost that information. That's the type 2 error. Same thing here. If you have no effect, you can either say there's nothing, or you can say there is something, but then you make a type 1 error. So the respective probabilities here in these columns is 1 or 100%. And that's important because essentially statistical power is essentially the 100% subtracted the beta. So we have here, that's alpha. That's the acceptable alpha, the acceptable type 1 error. This is beta. That's the acceptable type 2 error. And that acceptable type 2 error, well, should definitely never be larger than 20%, but commonly in study design, it's like about 10%. So you strive for statistical power of 90%. So, but what does that mean? So statistical power, you can calculate, and we're not doing this calculation. I'm not sure why they don't have this calculation in there, because it's a nice formula. So we have, what goes in there is population mean, population standard deviation, sample mean, sample size, and the standard error. So you will not know the population mean. You will not know the standard deviation. You may not know your sample mean, but you can estimate it. And that's the problem with power calculations. All of this you need to estimate. So how that practically looks like. So this is the formula nicely illustrates it, how that all is interconnected. So it's one formula where all of these components are contained. But you basically, what you do, you go back to the literature, or you go to registry data, and you try to get an estimate of that mean based on previously reported data. You try to get an idea what is the mean blood pressure in that population, what is the mean variability or standard deviation in that population, what can I expect to see as a difference for an intervention, for example, if I place an intervention, what is an expected to be expected difference from a before to after or between two groups. So you try to estimate all of this, and then based on that standard error conferred to by your intervention, you are estimating your sample size. And in study design, this is really what you can modify, because you determine how many subjects do I need to study to ascertain under these assumptions of population mean, population standard deviation, intervention, treatment effect, whatsoever, whatever components come into this, how many people do I need to study? And then, of course, you need to determine a critical set value and the raw mean to calculate this power. And yeah, so this is basically the percentage of the distribution of the means for population 1 that falls above that critical value. So you essentially, you mean to quantify by that probability of running into type 2 error. And you basically, you then inwardly aim for statistical power. And this is now illustrated here. Let's first talk about the four different ways how to increase this power. So we have an increase in alpha. So if you increase in alpha, that means that you're willing to accept a larger type 1 error. So that's increasing your P, your acceptable P value. So if you say, okay, so now it's not 5% anymore, now I'm okay with 10%, that's when you increase your alpha. You can turn a two-tailed hypothesis into a one-tailed hypothesis when you only are interested into increases in blood pressure or decreases in blood pressure, for example. So you make it a directional hypothesis. You can increase the sample size, and this is the low-hanging fruit, but that's also expensive. With every 10, 20, 30 participants more, you basically you have substantially larger costs. You need more logistics. You need another clinical research coordinator. It will take you longer. You will need a greater recruitment pool. You have a million things to think about. So that comes at a price. Or lastly, you exaggerate the difference between the levels of the independent variable. What does that mean? So basically, it's the independent variable in a cohort design or in a randomized trial. The independent variable is intervention or control. That's a nominal categorical variable, right? So if you want to exaggerate that mean difference, you have a problem in many cases because you would need to find a way to intensify your intervention. So you need a stronger intervention to get these two groups apart. And that's sometimes hard to do, sometimes even unethical. So here's the depiction, right? So you're having an acceptable alpha, and you have everything exceeding that from the population. That constitutes your power. So this pinkened area on top, that is conceptually your power. Same here. So if you increase your alpha, you're basically increasing that region that is not overlapping. So that's how you have to conceptually think about it. The same, obviously, when you do a one-tailed versus a two-tailed test, because now you have a two-tailed test, you have 2.5% on each side. If you have a one-tailed test, suddenly the 5% go in one tail, right? So you have a larger area of power. You can also increase the sample size, thereby decrease your variability. And that's the same way of depiction as we have had earlier with the effect size. So basically, it's the same difference, but by decreasing the variability, by increasing the sample size, you actually get again a larger overlapping region in relation. Or non-overlapping, larger non-overlapping. And then you can also increase the difference. For the aforementioned reason, this is a little complicated in many cases, so it's not easy to do in real life. Yep, and that's the thought experiment, right? Why is it actually important to understand the statistical power of your study? And this comes down to that table, and that's why I think this table. So there are this table and these 4 points. If you understand those and you can answer those on the quiz, I think that's sufficient. But that table basically gives you what you need. You have, in truth, a difference. This adds up to 100%. You make the correct decision. That's your power, and you subtract the probability of running into a type 2 error by producing a false negative result. So that's the relationship between power and the correct decision, the power and the type 2 error. And here you have a correct decision where you reject the null hypothesis, and you're accepting a false positive. Okay. Any questions? I think the relationship to sample size is really important to understand, because that's, you will hear, and whenever you read papers from randomized controlled trials, you will hear the term power calculation and sample size estimation. And that is really, in many cases, it gives you an assumption of what the researcher thought the effect size will be. So they give you an estimate, and they're basing this on previously published data. And based on that estimate, they will basically move forward, and they will then determine their sample size, or the overall sample. Good. So we can go back to this example, for example. So as said before, we want to speak again about the confidence interval. Actually, 605, 720. What else? Okay, central limit theorem. Talk about that. Confidence interval. Yeah. With the confidence interval, I think the most important thing is to understand the concept of the probability of including a population mean. The confidence, what does that actually mean? The confidence that I have to capture this population mean. So when I'm interested in a 5% alpha, and this is really how you can use this. You can use the 95% confidence interval for actually hypothesis testing as well. So if your population mean is contained in your confidence intervals, you will pretty much always, you will accept the null hypothesis. If you are interested in a 99% confidence interval, where you are looking at a critical set score of 2.58, you have the same calculation that you had for the 95% confidence interval. Oops. Not like that. G40. So you're basically adding now, rather than adding 1.96 multiplied by the standard error, you're adding now 2.5 then. No. G14. So you see here illustrated that as soon as you widen your interval and you thereby increase your confidence on that interval that you're capturing the population mean, that this will essentially widen also the numerical values. So now you essentially, that interval has widened, and thereby you become more confident that your confidence interval will contain the population mean. If you would go for an alpha of, let's say, 10%, you would essentially now use a different set score. And if we quickly look at the set score table, we know that 90%, that means like 5% in both directions, right? So now if we are looking for 5%, we're finding these 5% here at 1.65. So remember how to calculate, how to interpret this set score table. So basically it starts with the rows, it starts by 0 and it goes to minus 3.4 on this one, but it will basically approach in infinity, it will approach the x-axis. But we're having here the second decimal being found along the columns. And if you're interested in 10% distributed on both tails, you would need to go and find this respective corresponding p-value, which would be found here was 1.65 or 1.645 almost. So if we are taking now 1.645 as our threshold, so now this is locked in, this is locked in, this is locked in, good. This is locked in. So if we're extending this, we're basically using now the example of a 95% confidence interval. And that comes back to the depiction that said, like, you can calculate this confidence for any probability you're interested in. You would change this now to 1.645. You also get consistently changed confidence interval, which basically is now narrower, because within this range, you are less confident you will actually capture your population mean, which is just consistent with widening it, right? So yeah, so this is all I had for today. I think we can conclude. Any questions? Please don't forget that Wednesday we're doing remote. So same time, I will send the Zoom link. Oh, Zoom link will be on Canvas. All right, have a nice evening.